So I'm back from Mumbai with the long-awaited, promised proof of the Abelian property, which I claimed I would prove for you twice already. So I'm going to follow through on, and then we're going to take the proof and try to squeeze it, as much juice out of it as we possibly can, and see where that takes us. So. We've seen roto-routing in Rahul's talk. So you can think of the story I'm about to tell you either in the context of roto-routing or in the context of the Abelian sandpile, whichever you prefer. So this part of the story is exactly the same for the two models. So I'll write it down for sandpiles to be, continuing my earlier talks. So given a sandpile on a finite graph, so we talked about stabilizing by topplings, but we never carefully checked that that's really well defined. So that's what we're going to do now. So how do you stabilize by topplings? Well, you pick a sequence of vertices to topple. So, as usual, everything will take place on a finite connected graph. So let's take a sequence of vertices, and we'll say sequence X is legal for the sandpile S if. Well, what does it mean to be legal? It means I really have enough chips to actually carry out topplings in this order. So first, I'm supposed to topple x1, and in order to do that, the sandpile doesn't like to topple. It's not supposed to topple unless it has at least degree x1 chips. Okay, so that's the first requirement. And then we move on to x2. And well, now we've changed the sandpile a little bit, right? So it won't be, now we have a new sandpile, I'll call it S1. It's the thing we get after toppling X1. And we're going to look at how many chips it has at X2. And to be legal, it better be at least a degree of X2. And so on. So what is S1, just to spell it out? S1 is what you get by toppling X1. So it's the original S plus Laplacian of delta x1. Okay, and so on. S2 of x3 is at least degree of x3. Dot, dot, dot. S m minus 1, xm is at least degree of xm. So legal means, this whole sequence of m inequalities holds. And, the SIs are defined just how you think they are, right? So, S2 is S1 plus delta x2, and so on. Okay, so notice there's something absent from these conditions, which is legal doesn't make any reference to whether we finished or not, okay? All we have is inequalities in the same direction that say there are enough chips to do something, right? You're not supposed to stop toppling until everything is stable, right? So that will come in next definition. So we'll say a toppling sequence X is stabilizing for S if when you do all these topplings, nothing else is allowed to topple. So unlike this where I had to write m different inequalities, one for each toppling, this one I can get away with a single inequality, and it looks like this. S plus Laplacian of u is pointwise smaller than degree minus 1. And what is u? It's the function that counts how many times a given vertex appears in this sequence. So u is, well, it's the sum of the indicators of these vertices, delta x1 plus delta xm. So these two conditions, I mean, they're breaking apart, the upper and lower bounds you need on S, right? The legal gives you all the lower bounds you need, and the stabilizing gives you all of the upper bounds you need. I mean, okay, it looks like only one, but it's actually one inequality. It's an inequality of functions on vertices. So for each vertex, there's an inequality. So what the sandpile actually does is both legal and stabilizing, right? So I'm going to make a maybe somewhat strange-seeming definition. I'll say that the sandpile stabilizes if there exists a finite stabilizing sequence. If there exists stabilizing x for S. And like, the reason I say this is a strange-seeming definition is, well, it doesn't make any mention of legality, right? So it's not clear, at least unless you start thinking about it, that existence of a stabilizing x means that when you run the sandpile, things are eventually going to stop, right? Because this inequality is, is just an inequality of functions. It doesn't bother to check whether things were legal. But the reason this is an okay definition is the following lemma. So this lemma is one version of the Abelian property. Okay, suppose S stabilizes. So there exists some stabilizing sequence X. Then for any X that's legal, and any y that's stabilizing, we have that x is a permutation of a subsequence of y. Of a subsequence of y. So in particular, there's an upper bound on the length of legal sequences for S, right? Just take your favorite stabilizing sequence, which by assumption it exists. And then any legal sequence, so it has to be a permutation of a subsequence of that. So it has to be at most the length of that stabilizing sequence. Okay. So we'll prove this in a sec, but let me state the rest of the lemma. So the rest says there exists a legal stabilizing sequence S. So it's like getting something for free, right? So we only supposed S stabilizes. So we only supposed existence of a finite stabilizing sequence. But according to the lemma, that implies there exists a legal one. And 3 will be, well, an immediate consequence of 1 and 2, any 2 such are permutations of one another. So we start with like the smallest possible assumption, just existence of a stabilizing sequence. And then we get a seemingly stronger conclusion that in fact there exists a legal stabilizing sequence, and that legal stabilizing sequence, up to permutation, it's unique. Okay, so it was harder to state than to prove. So, how do you prove something? The advantage of having like almost no hypothesis is, there's not very many choices of how to go when you go about proving it, right? It's not like, where am I going to use this hypothesis and that one? I mean, all we have is that it stabilizes. So, okay, so what are we given? We're given X legal and Y stabilizing. And I want to prove X is a subsequence of a permutation. No, is it permutation of a subsequence? I guess that's equivalent, right, of Y. So, okay, so I'm going to induct on the length. So, let's look at S of x1. How many chips are at x1? Well, X is legal, so, there have to be enough chips at x1 to topple it. So that's at least a degree of x1. On the other hand, Y is stabilizing. So if we do all the topplings in Y, then we're going to get something strictly less than the degree. So this is strictly bigger than S plus delta y1 plus. So I do all the topplings in Y. And evaluate at x1. So I used both my hypotheses here, which is a good sign, right? So I used that that X was legal, and here I used that Y was stabilizing. Y stabilizing, and yeah, well, that's all I have to work with, so this better be enough. So, what are we going to do? How are we going to induct? So, the point is that Laplacian has a simple sign pattern, right? So, it's negative on the diagonal, but it's non-negative everywhere else. So, when you topple a vertex, you're taking chips away from that vertex, but everywhere else, you're not taking any chips away. You may be adding, you may be doing nothing, but toppling will never take chips away from a vertex that is not right where you're toppling. And so, in particular, I claim x1 has to appear somewhere in this sequence of y's, right? So it follows that x1 equals yi for some I. Why? Because if not, then all these topplings were different vertices, were not x1, and so they could only add chips to x1, they couldn't take them away, and so we couldn't end up with fewer than the degree chips. Okay, and that's it. So now we're going to cross off x1, cross off yi, and so you'll get two smaller sequences. Cross off x1 from x, and yi from y. And then the result is that, well, what you get will be, so you get a shorter sequence, x prime, which just omits x1, and it's still legal for, not for S anymore, but for the new sandpile S1 that you got from toppling x1. And this, likewise, this new y will be legal not for S, or will be stabilizing not for S, but for S1. Okay, and so by induction, x prime is a subsequence of a, is a permutation of a subsequence of y prime, and so the same is true once I put the x1 back in. Done my induction. Okay. I hope that was clear. Like, it all comes down to the sign pattern, right? So if you put some negative entries off diagonal in delta, that will break this proof in a kind of irreparable way. But that's sort of all there is to it. So let's see how the other things follow. So those are basically immediate, right? So how do I know if there's a stabilizing thing, that there's actually a legal stabilizing thing? Well, once I have a stabilizing thing, then as I already pointed out, part 1 says all the legal things are bounded in length by that stabilizing thing. So let's take a maximal length legal thing. Take x legal of maximal length. Well, then it must be stabilizing, because otherwise, if something were unstable, you could topple that thing to get a longer legal sequence. So then x is stabilizing. So in fact, there is a legal stabilizing thing as claimed. And 3, well, 3 is immediate from 1, right? So, you know, if x and y are both legal and they're both stabilizing, then you just apply 1 both ways. We'll apply part 1, you know, twice. So x is a subsequence of a permutation of y, and y is a subsequence of a permutation of x, so they must be permutations of each other. I keep saying subsequence of permutation, but I mean permutation of subsequence. Okay, so this part 3 is what's usually, what usually gets used is part 3. Well, I guess I'll call this a definition. Maybe this word came up already, odometer. So the odometer and stabilization. Okay, so stabilization, you can guess what it is. Stabilization, well, I guess I used this notation, curly S of S, is the sandpile that you get by toppling your favorite legal stabilizing sequence. So one way to write it is S plus delta U, where U is the counting function of I'll just write it in symbols. So U counts how many topplings there are. So U is delta x1 plus delta x. M for any legal stabilizing X for S. Point being, it doesn't matter which legal stabilizing sequence you pick because, well, they're equal up to permutation, so you might permute these terms, but the sum will be the same. And this U is the thing we call the odometer. So this is called the odometer of S. So Jim Propp is the one who came up with the name odometer. He was, I don't think he was being too serious about it, but he was just imagining there's like in the car, you know, it measures how many miles the car has gone. So imagine each vertex has a little counter that, you know, increments by 1 every time the vertex topples. Okay, so usually, often, you know, part 3 is the, you know, the real thing that people call the Abelian property. But, you know, part 1 is kind of formally stronger, and sometimes that extra little strength is useful. Why is it formally stronger? Because it kind of, you know, it doesn't require both X and Y to be both legal and stabilizing. It's kind of, you know, it's 1/2 of the inequality. As you know from other contexts, like, I don't know, I mean, like, there's lots of things you know about harmonic functions, right? But sometimes you only have superharmonic functions, and so you want to, you know, prove something about harmonic functions via 2 inequalities about superharmonic functions. It's that sort of thing. And one sometimes goes by the name least action principle when you state it in the following form. So right? So this is this part, least action. So I'll call this another lemma, but or maybe corollary. Yeah, corollary. So it's a corollary of this lemma, and it does the following. So suppose again that S is a sandpile that stabilizes. Then its odometer, U, satisfies the following kind of curious optimization problem. So for each vertex X, I can look at how many times X toppled, and that will be the infimum over all functions, let's say W. And what should W satisfy? It should be non-negative, integer valued, because after all, it's kind of supposed to count topplings. And it should be a recipe for stabilizing the sandpile. So S plus delta W should be less than or equal to degree minus 1. Oh, maybe, yeah. So I have an X on this side. So I wrote that because I want to emphasize it's a pointwise infimum. So maybe I'll write it like this. U of X is infimum of W of X, such that W is a function V to N, and W obeys this inequality. So depending on your background and tastes, this thing is either very familiar to you or it looks bizarre. So well, I'm used to it by now, but I think it would have looked bizarre to me, in grad school. I guess by the end of grad school, I was like comfortable with it. But you've got this family of functions, and you've got three constraints on the functions, right? I mean, maybe it's clearer to spell out these constraints like this. So W is greater than or equal to 0, because it's natural number valued. And then you've got this Laplacian constraint. And then I didn't explicitly in these two equations say that it's integer valued, but that's kind of key. So let's make that its own little line. So W is integer valued. So if sort of separates it out more cleanly to think of it as three separate conditions. Okay, so these are the constraints. You get this big family of functions, and you take their pointwise infimum. Okay. But if you come from PDE or like numerical optimization kind of worlds, then you're used to seeing things like this, and you recognize what in PDA they call the obstacle problem. So that problem is it corresponds to a physical situation like you have a net that's kind of hanging down, and if there's nothing blocking it, then there's some simple equation that the interior of the net has to obey, and then the location of the frame it's hanging from gives you the boundary conditions. But now imagine your net is hanging in such a way, there's something like blocking it underneath. Like I'm hanging it above this table, and so it wants to hang below the table, but it can't. And so there's kind of two phases. There's a phase where part of the net is flat on the table, and then the rest of it is kind of hanging from the frame to the flat. And so what's tricky and fun about these problems is you not only have an unknown function, which is the height of the net, you also have an unknown domain, right, which is like where you change phase. So there's this, the net is, it's trying to hang as low as possible subject to some energy constraint. And like, it's allowed to land on the table in whatever shape it wants. So you don't know in advance which parts of the net are going to be flat on the table and which are going to be above it. Those you sometimes see called free boundary problems. So this is, it's like a discrete free boundary problem. Okay. And the kind of novel feature of this free boundary problem is the Z. Okay. So, in PDE, people don't work with Z-valued functions because they're working in over the reals, and it's natural to use continuous functions and be able to differentiable functions, and what would it even mean to have a PDE with integer-valued functions? So there's a certain sense in which this Z is responsible for most of the novel, interesting behavior of the sandpile. So a good first reaction to seeing a problem like this is like, what happens if I drop the integrality constraint? Okay, so I'll just allow W to be real valued and see what happens. Well, we already saw some talks about what happens. So anyone have a guess? Or so it corresponds to some other model that we heard about earlier this week. See, Leo is nodding, so. Okay, Violetto. Which, well, right. So it makes sense, right? Chips are integer valued. You can't split them up, but divisible sandpile is you're allowed to split up your chips, right? So if you replace this by R, you would exactly get the constraints for the odometer of the divisible sandpile. And so I mostly stopped giving slide talks because they make me rush, but this is one place where I wish I had a slide. I'll try to show it tomorrow, because it's very instructive to compare side by side an abelian and a divisible sandpile, started from the same initial condition. So let's start it from, say, n chips at the origin in Z2. So that's our S. So, well, we know, or if you haven't seen the picture of what this does in the sandpile, then I'll show it to you tomorrow. So it makes a beautiful kind of complicated fractal looking picture with a lot of rich internal structure. And if you do the same initial condition for visible sandpile where you have to split up your chips, you lose all the internal structure, and you get a limit shape, which is a disk. Okay? So it's Euclidean disk. And in fact, it's even very close to a disk. You know, the error in the radius is constant. It's not even growing as n goes to infinity. So if you want, if you want to talk about universality, right? So Abelian sandpile. So that's the situation where we have the integrality constraint. You get, there is a limit shape by a theorem of Pegden and Smart. Limit shape as n goes to infinity. And did I mention this already? I can't remember. But anyway, there exists a limit shape. We know that. And, well, we're certain it's not a disk. Nobody actually, bothered to write down a form proof that it's not a disk, but it's definitely not. Not a disk. Which is, a symptom of non-universality, right? Universality, if we want to forget the details of the lattice, okay? And if we forget those details, then we ought to get something rotationally symmetric in the plane. And the only compact that's rotationally symmetric about the origin, which is special because that's where we started, is a disk. So this is, it's not universal. There's some lattice dependence. That survives in the scaling limit. So, traditionally you would think of that as a negative feature. It's like maybe universal models, maybe they're more important in a sense because by studying one model, if you know it's universal, then most of the details disappear in the limit, and so you can say that your findings are relevant for a big class of models. Whereas here, well, the model is kind of special, and even when you zoom out and you pass to the n goes to infinity limit and you rescale so the lattice mesh is going to 0, somehow this sandpile limit, which lives on R2, it still remembers that it came from a square lattice. And one thing I will talk about tomorrow is how can we quantify that memory. So, there's a certain object that kind of encapsulates all of the lattice dependence in this particular model, the abelian sandpile on Z2. And we have a very precise description of this object, and in a sense it encodes all of the lattice details that are not forgotten in the limit. And it's kind of the tip of the iceberg because for most lattice-dependent models, we have no idea how to quantify which details are important in the limit. This is one of the only ones where we have a good handle on it. Even abelian sandpile, if you just change the lattice, then we don't have a good understanding yet. So that's abelian sandpile, and the contrast is divisible sandpile, where you replace the z by an r, well, again, there exists a limit shape, and it's a ball, or a disk. Limit shape is a disk. And that's not hard to prove. I'm not going to prove it for you because it would take up too much time, but I'll just tell you in 10 seconds that the main ingredient of the proof is the green function of Z2, or it's called the potential kernel sometimes in Z2. Because in Z2, your random walk is recurrent, so you can't actually count expected number of visits of a random walk will be infinite. But you kind of renormalize it to make it finite, and then you get this function on Z2, which basically its asymptotics are very well understood, and the first order asymptotic only depends on the L2 norm. And not only that, but there's a next order term which you would expect to be the error, but that term is 0. So you have to go 2 orders lower to see the error term. The error term is incredibly small. So of course the function, since it's defined on Z2, it can't be an absolutely perfectly rotationally symmetric thing, but it's really, really close. Okay? And you express your sandpile in terms of that green function, which is really close to rotationally symmetric, and the other ingredient is a quadratic, which is perfectly rotationally symmetric, and that's how you can prove it's a disk. Okay, so I guess what I want to emphasize before moving on is it's not really what you would expect necessarily to have this giant difference in behavior between integer and real values. I mean, well, you could argue both sides, right? So one side would say, in optimization problems, it's a pretty well-studied, well-known phenomenon that it's hard to optimize integer-valued things, and if you instead relax the problem so that you're optimizing real-valued things, then you can get a bound in one direction. And sometimes there's a big gap between that bound and the integer truth, and they call it the integrality gap. And okay, so this is, if you like, it's some manifestation of that integrality gap. But the gap is just surprisingly large. To argue the other side, I mean, we're taking a scaling limit. So, when I take n larger and larger, my odometer function, my w, is going to grow, right? So this w is diverging, and if something's diverging, it shouldn't matter that much, you would think, whether it's integer value. I mean, what's the difference between 1,000,000 topplings and 1,000,000.1 topplings? It seems like a tiny rounding error, right? So the big difference in behavior, it's some interaction between, you don't just have one integrality constraint, you have them at every lattice site, and somehow they interact in an interesting way to make a big difference between the two situations. Okay. I know what else I wanted to say. So, one way to think about this infimum is well, it's the smallest the odometer could possibly be, right? Because certainly the odometer is such a function. If you take S and you add Laplacian of the odometer, you're going to get the stabilization of S, which by definition it has to be smaller than degree minus 1. So U is actually a member of this family. So the infimum is a minimum. And I guess the only reason I didn't write minimum is you could wonder, well, what happens if S doesn't stabilize? And if S doesn't stabilize, then, well, what is that saying? That's saying there's no stabilizing sequence, and therefore there is no such W. So this family of functions is an empty set in that case. And so what's infimum of the empty set? Well, infinity. And that's accurate too, right? So that's saying if you don't stabilize, then your odometer is infinite. Every site topples infinitely often. So with infimum, I could erase this assumption that S stabilizes, and this is still accurate in every case. Now, returning to the case when it does stabilize, so U is a member of this family, so somehow it's saying that U is very efficient at stabilizing this sandpile. So you can't beat U even if you are only focused on one vertex. So like I could like pick out the origin and be like, I really don't want the origin to topple very much. I'm going to let other vertices do extra work if they have to, okay? But I'm going to try to stabilize my sandpile with toppling the origin the least amount possible. Well, it turns out the odometer does that, and it does it simultaneously for every vertex. Okay. As other speakers have emphasized, the Abelian property is a kind of key ingredient in a lot of proofs, not only in this model, but in related models that are lucky enough to have the Abelian property. And so in that kind of situation, when you have some simple lemma that you use over and over again, it's worth trying to squeeze it to see if you can get any more out of it. And one way to do that is like reinterpret what the symbols mean and what the words mean. So, I stated this for sandpiles, but you could just as well take S to be a, say, a rotor configuration on Z2, like we saw in Rahul's talk. And then, what does stabilizing versus exploding mean for a rotor configuration? Well, stabilizing means the odometer is finite, so you visit every site only finitely often. Exploding means odometer is infinite. Okay, so it's exactly, stabilizing is transient, and exploding is recurrence. Okay? So, and what does legal and what does stabilizing mean for rotor? Well, so you've got some rotors in Z2. Each site has a rotor pointing to one of its neighbors, and then you've got some chips, maybe only one chip, but it could be more. And a legal move would be, well, you point to a site where there is at least one chip, and you you update the rotor there, and then you move the chip. So legal corresponds to, there is actually a chip available at the site where you want to move. And stabilizing means after you've done all your moves, there are no more chips. So like in the case of Z2, if you manage to stabilize, then that's saying that, well, you did an infinite sequence of rotor moves that made your particle escape to infinity. So there's nothing left to do. And we've reinterpreted all the words, but then the proof works verbatim for that interpretation. So for a while, that was kind of the, that was kind of the situation that, everybody knew that this argument works in a lot of situations, and you get a feel for like when it's going to apply, and then you tweak it slightly for the situation where you need it. And, that works fine, but there's some value in trying to write down like, the most general situation where it works. And so I'll tell you one situation where it works that's kind of medium general. It's not the most general, but it encompasses rotor and sandpile and a lot more. So these are the unary Abelian networks. Yes? Okay, good, right. Yeah, so So if you want to write U as a supremum instead of an infimum, then, as Leo points out, it's the infimum, or it's the supremum of all, let me use a different letter like V, such that, V is the counting sequence, or V counts a legal sequence for S. So yeah, that shows maybe the duality between legal and stabilizing, right? So it's the smallest stabilizing thing, and it's also the biggest legal thing. More comments, questions? Okay, so here's another situation where the same argument works verbatim. I sometimes I like to play this game once in a while where I take a proof that's particularly useful and not too long, and just try to reinterpret everything, all the words and symbols, in such a way that the proof works without changing a single word or symbol. So that's what we're going to do here. Hopefully it succeeds. So sometimes you have to change some minor things. So this comes from Deepak's idea that maybe these particle systems could be useful to compute something. Okay? So how would you make sense of that idea? So one thing we can do is put a finite state space at each vertex. I'll call it Qi for each vertex. So for example, in the rotor case, the local state of a vertex will be the rotor that points to one of its neighbors. And suppose you're given a transition map, so that tells you, how to update your state whenever you fire a chip. Okay? So state transition. Now, so far, this map is only half the story because it's telling me how to change my local state, but it's not telling me whether I'm supposed to send any chips to my neighbors. Okay? So we need another function to encode that. Let's call it Tij. So, and that will be for each edge. So each edge, we're given a function that says, okay, if you're in a particular local state, then you might want to send some chips along that edge. And I'll let you send 0, but I'll also let you send 1 or 2 or 3, any natural number. Right? So this is we called it message passing. So you could think of a chip as a very primitive sort of message. It's just like a poke, All chips are indistinguishable, right? But, you could send a message to your neighbor that's just like, hey, have a chip. So, or you could send a message like, hey, have 10 chips. Okay, so suppose you're given all this data, right? You've got a finite set for each vertex, a state transition function and for each vertex, and a message passing function for each edge. Then that defines, in what I hope is an obvious way, a discrete dynamical system like sandpile or rotor. But sandpile and rotor correspond to two special choices of the TIs and TIJs, and you could vary them and see what else you can get. And okay, before I erase this, let's see if the proof applies without changing anything. So we want to prove an Abelian property for systems like this. which at first seems like way too optimistic. I mean, obviously, if you've got a bunch of finite automata talking to each other, it really ought to matter, like who says what in what order. And indeed, it usually does matter, okay? However, in this situation, my automata are of a very simple type where all they can do is receive and send chips, and chips are indistinguishable, okay? So that's the unary in the name. So in that situation, it turns out all of these unary systems with no conditions whatsoever on the t's they're all abelian. So let's just spell out like what would legal mean in this setting. Well, I guess I should say like what's a state of the network. So my network, you know, it's the graph. The data for the network is, you know, the graph and the TIs and the TIJs. So this N is an abelian network. Okay, and then what does the network actually do? Well, so if you want to specify the full state of the whole network, we use this notation x dot q for the state. So x is a vector of integers that tells you how many chips are at each vertex. So this is the chip configuration. And q is a vector of states that tells you the local state of all the vertices. So q belongs to like the Cartesian product of these qi's. Okay, so that's the full state of your system. And then what does the system do? Well, a legal move says you can point to a chip and then so legal move let me say what a move is before saying what a legal move is. So I don't know, maybe I'll call it a firing move. So a firing move corresponds to, in the sandpile case, it will be, you might think it would be toppling, but that's too much. That's like several moves. So a firing move is smaller. It's just absorbing one chip and toppling if you can. That's a sandpile firing move. And a rotor firing move is updating your rotor and following the rotor. Okay, so what is a firing move in this general setting? You do, so from x dot q, let's say, if you want to fire a particular vertex I, then you end up in a new state of the network, x prime dot q prime. And how are these related? So, well, first let's update the state. So q prime I, so the state at I should be updated compared to what it was. So I take my transition function and I plug in the old state qi, and I get some new state qi prime. And I don't do anything to the other states. Let's say qj equals this when j equals I, and otherwise it's unchanged. Okay, so that tells me my new state. And then I need to say what happens to the chips. And that's going to be my message passing function tells me that. So, so if I want to compare like the new chip counts to the old chip counts, then, well, at vertex I kind of used up one chip in this operation. So I'm going to lose one chip. So x I minus 1 if j equals I. At the neighbors, I might gain some chips. Oops, I put the xi here. So I lose one chip at vertex I when I fire I. I might gain some chips depending on the message passing function. So I have to look at Tij of my new state, Qi. And that's how many chips I'm going to gain at all the neighbors, or at each neighbor. And then if you're not a neighbor, you're unaffected. So you could see some kind of resemblance to the Laplacian situation. Like you're only losing chips at the vertex where you fire, and everywhere else you're either staying the same or you're potentially gaining chips. And as we saw in the proof, that was the key to making the abelian property proof work. Okay, so that's the dynamics, and just as with the sandpile and the rotor, we appear to have choices of like which things to fire in what order, and to make the proof work without changing anything, we should say that legal means there's always a chip available to be fired. So that's saying like xi is positive. Right? It's legal to fire I if there's at least one chip there. Otherwise, this move would take your chip count negative. And stabilizing says after you do all your moves, there's nothing left to do, right? So that's just saying that all your chip counts are less than or equal to 0. So those are my definitions of legal and stabilizing. And then, yeah, so I claim, except for a notation collision of x there and x there, which is kind of unfortunate, nothing needs to be changed in the proof. Well, okay. I mean, I guess, this line was sort of specific to sandpiles, right? So you need a few changes in this line, right? So you need to change, like, I guess S became X. Okay, so I won't do the changes because it'll be a mess. But basically, same proof. Okay. So in the last few minutes, I want to tell you some theorems that Ben Bond and I proved about abelian networks. They're pretty easy to prove once you have all the definitions, right? But I think they're worth knowing. And then I want to, well, maybe I can save it for the discussion, kind of speculate a little bit on, when is it useful to build a theory like this and when is it a waste of time? So okay, so I'll save that for the discussion because I think it should, hopefully some people will disagree with my viewpoint and we can duke it out. So, yeah, so let me state some kind of basic theorems about abelian networks. So the first one is the abelian property. That they were kind of designed to make the proof of the abelian property work. But somehow the most basic thing you could ask about them is, the halting problem, right? So in any model of computation, the halting, deciding whether a program stops is kind of, it's a very basic thing to want to do, and it's kind of measures the power of the computational model, right? So let's say I give you a finite abelian network, and I give you its states, I give you its x and its q, and I want you to tell me, is it going to halt? So what does it mean that it halts? It's just the same dichotomy, stabilizing or exploding. So if infinitely many moves, I can eliminate all the chips then I halt. So, halting problem. So given n and x and q, does the computation halt, or does the system stabilize or explode? Like many of the questions we heard about this week, you can phrase them as instances of the halting problem. And, well, let's start with finite networks, because at least in the finite case, there's going to be some algorithm. It might not be efficient, but like if each state space is finite and there are finitely many vertices, then one would think, and the only infinite thing potentially is the x, right? Because chip counts could grow unbounded. But in that case, if they're growing, you would think it's not going to halt, right? So there ought to be at least an algorithm in that case. And there is. Okay, so let me tell you two things we know. So one, first let's ask the problem of halting on all inputs. So all these theorems are joint with Ben Bond, who was an MIT undergrad when we started this project, and went to Stanford for grad school and now works in, I think last I checked he was at a tech company. So maybe they're secretly using his expertise to do like asynchronous algorithms or something. Okay, so if you have a finite and irreducible Abelian network, it won't define irreducible, but you can imagine approximately what it means. Halt on all inputs. If and only if a certain eigenvalue is strictly less than 1, and I won't tell you exactly what this lambda is, but basically the way you get it is from the description of the network, you build a matrix that encodes, like, on average over all the states, how many, the frequency of sending chips from I to J. And so we call that the production matrix, and it's a non-negative matrix, so it has a Perron eigenvalue, the biggest one. Perron eigenvalue of production matrix. So basically, there's this matrix that tells you, like, on average, if you kind of cycled through the states, did a full period of all the states, then it would tell you exactly what's happening. And the details of the fine details about, which transitions and which bridges are passed when doesn't enter into this question of halting on all inputs. So the only thing that enters in is this kind of averaged out production matrix. All right, so that's kind of, it's nice to have a simple criterion like that. If you want to ask the more delicate question of whether it halts on a given x dot q, then it becomes harder. So it's still decidable, but it's NP hard already for sandpiles on directed graphs. So halting on a given input is NP hard. Well, in that case, it's NP complete. It's also in NP. For a particular special case of an abelian network, namely sandpile on directed graphs. And this is kind of an interesting story, which, I mean, maybe the physics significance of directed graphs is kind of dubious, so I won't go into the story, but basically, unlike undirected graphs, you can have stabilization that takes an exponentially long time on a directed graph. And that doesn't prove it's NP complete, because maybe there's some fast way, without actually performing all those exponentially many topplings, that you could predict whether it's going to stabilize. But we showed there isn't. But there's something still open here, which is, I find intriguing. So to be more accurate, I should say directed multigraphs. So there may be multiple edges. And in fact, the hard instance, if you trace through the proof, you get that the entries of the adjacency matrix are blowing up. And so the hard instances potentially are hard because of very large edge multiplicities. And so I'll just mention this open problem is, what about simple directed graphs? So can you decide in polynomial time whether a sandpile on a simple directed graph, so edge multiplicity 0 or 1, is going to stabilize? You can't do it naively just by topplings, because it's easy to build directed graphs that take exponentially many topplings to stabilize, but maybe there's some clever trick that will let you decide it otherwise. I would guess it's still NP complete, but it's a nice problem. All right, so that's halting. And okay, I will stop here for the discussion. So let me, let me invite some questions and comments, and then give you some options for what we can discuss if those die out. Yeah. Yes, right. Right. Yep. Yeah, so I'll repeat Leo's comment so in case you need it amplified. So for this halting question, we assumed finite state space. And I guess I wrote it even in the definition. So if you wanted abelian networks that can incorporate randomness, then well, there's two ways to think about it. So you could have an infinite stack of instructions at each vertex that tells you what it's supposed to do, the nth time it performs a firing. And then, you could think of that as sort of some quenched randomness. So you could take those sequences to be IID, say, and then view your thing as an abelian network, but with infinite state space. And a lot of what we show about abelian networks applies in that setting too, of countable state space. So the other thing you could do is, put a probability space into these maps. So you could say, well, the transition depends on some additional randomness, right? So we call that a stochastic abelian network. And one of the items on my to-do list is to write kind of basic foundational paper on these stochastic abelian networks. And like, it never quite gets to the top of the list. Instead, like, what happens is, see, one advantage of this perspective is you can see how much larger the space of possibilities of models is than the currently studied ones. And then so I get interested in some particular point in that space and go work on that. So if somebody wants to do that with me or just do it on their own, that would be awesome. Otherwise, I'll do it eventually. But there should be a basic theory of stochastic abelian networks. And I expect it will have some, like this theorem, some not too hard to prove, but kind of interesting basic theorems. For example, branching processes are stochastic abelian networks. And they're very simple ones, so their underlying graph is only a single vertex. So, you branch by sending 0, 1, or more chips to yourself. That's like, an individual having offspring. Okay? And so you can get multi-type branching, and you can get, branching processes with states. So it's kind of like whenever an individual is born, the environment changes, and so the offspring distribution can change. So you get all kinds of, both known models like branching processes and kind of weird generalizations of them that maybe haven't been studied. And I don't know, I think there's a lot of interesting territory there. And of course, it also includes, Mana model and Oslo model and activated walkers. So the models we've heard about this week. It's not as exciting, right, to develop some general theory about a class of models where, like, you would be much more excited to prove a theorem about just one of them. There's so many exciting conjectures, like the ones from Chris Hoffman's talk. They were just about one model, okay, maybe two, activated walkers and Mana model, right? Like, it would be very exciting to prove some of those conjectures. I see this theory building as something that's like, it's valuable when you've been trying too hard and failing to make progress on whatever problem you're currently obsessed with. It's like, it's a good way to take a break, do something very different, and you won't get as discouraged because, it's easier to make progress. And sometimes it's maybe more likely to give you a good idea than it would be to just keep bashing your head against the same hard problem. So, yeah, so my punchline about useless theories is that even if the theory you develop ends up not being useful for the problem or problems you developed it for, it might still have been worthwhile to develop it because in the process, you're kind of giving yourself the opportunity to solve those problems. So like, I can imagine, although it didn't happen yet, that, I can imagine someone actually uses abelian networks to prove a deep theorem. That would be great. And if you feel inspired to do that and succeed, then I will tell everyone how brilliant you are and write you a glowing recommendation letter, and everyone will want to hire you. So you should do it. But if that doesn't happen, then I still think it was useful to develop the theory because it shows all these other models one could study, and it's also the time spent developing it. It's like, how are you going to maximize your chance of getting a really good outside of the box, like radically new idea, right? If it's radically new and it's going to come from some unexpected direction, right? So you need to like force yourself to think outside of the box. But that's like hard to do. It's like the pink elephants thing. If I tell you, don't think about pink elephants, then you immediately visualize an elephant, right? And so if you just tell yourself, I got to think outside the box, I got to do something different, it's not very effective. So doing these kind of exercises, like taking a simple proof and reinterpreting all the symbols in it, it's like a different sort of thinking, and at least it's time you're spending doing math. So you're thinking about something related to what you want to do, but not as difficult, and so maybe it's more likely to trigger the idea you need than just going head on at the problem. Okay, so Yeah, that was my philosophy of useless theories. I didn't get to state all the theorems, but that's okay. More discussion?
Anyone with any more questions? All right, if not,